Hi, I'm Serrano and this is a friendly introduction to linear regression. This is the first video of a series of 3 videos that I'll be making. The first one is on linear regression, the second one on logistic regression, and the third one on support vector machines. But here's the interesting thing. Normally when we see explanations of linear regression, they involve linear algebra, matrices, derivatives, calculus, error functions. To me, this is way too complicated. To understand linear regression, all we need is a visual mind. The way I like to see it is with points and lines, and points talking to the lines and lines moving around to fit the points better. So let me show you what I mean by that. So first off, what is linear regression? I like to look at linear regression by looking at this example, housing prices. So let's say that there are 5 houses, house 1, 2, 3, 4, and 5, and house 1 has 1 room, house 2 has 2 rooms, all the way to house 5 that has 5 rooms. And we own house 3, and we want to put it in the market for sale, but we don't know what the price would be. So we want to find a good estimate. So in order to do that, we look at the price of similar houses and we try to guess what the price would be. So we look around and find that house 1 costs $150,000, house 2 costs $200,000, house 4 costs $300,000, and house 5 costs $350,000. So the question is, how much do you think house 3 costs? Feel free to think about it. Feel free to pause the video. The answer that I have is $250K. That's the best estimate we can come up with. It may not be that price, but it's the best estimate from this model. And why do we think it's this model? Well, it roughly seems like the houses have a base price of $100,000 and each extra room costs $50,000. So in this case, it's 100 plus 3 times 50, which is 250. Mentally, what we did was exactly linear regression, because what we did was this. We put houses 1, 2, 4, and 5 in a plot where the horizontal axis has the number of rooms and the vertical axis has the price. And it seems that the rule for price is this line. And so we put the house 3 over the line because that's the best estimate we can have. And that gives us a price of $250,000. So that's pretty much it. That's linear regression. It's fitting a line through a set of points and then using that line to make a prediction. Now in real life, prices are not that easy to calculate. There will be other factors. So maybe the data will look a little more like this. But we can still fit a line that goes really close to all the prices of the houses. So that's the point of linear regression. In a more general case, we have a bunch of points that they sort of look like they're forming a line. And the idea is to find the line that passes the closest to these points. And in the same way that we use this to calculate the price of a house, we can use this for numerous applications anytime we need to calculate a number. For example, in finance, we can use it to calculate the price of a stock. In medicine, we can calculate the lifespan of a patient or the spread of a virus. There are many applications, and I would encourage you to think of some. But now the question is, how do we do this? How do we fit a line through a bunch of points? How do we find the line that goes closest through a set of points like this one? Now, for a human, if there's not too many points, this is easy to eyeball. But when data gets complicated, it's not that easy. And even worse, for a computer can't really just find a line that goes through a set of points by looking at it. It has to have an algorithm. It has to have a procedure. And in rough terms, this is what our algorithm does. First, it throws a random line. And this random line will probably not work very well. But then, it starts slowly moving it closer and closer to the points until it gets to a point that works. So let me be a bit more specific. What we're going to do is we're going to throw a random line and then we're going to start asking the points, what do they want? So let's pick a random point and ask it, what would you like? Well, this point says come closer because the closer the line is to this point, the better a fit it is for that particular point. So we listen to it and we move a little closer. Then we pick another point and we ask it. And it says again, come closer. All of them will really say come closer. So then we move the line closer to this particular point. And then we keep doing that. Come closer, we move it to this point. We accidentally passed it, but this is okay. Then the other one says come closer. Then this one says come closer, and until we're done. Now notice that we picked each point once. We could repeat points. We could pick a random point each time and maybe have some points that never got picked, maybe some that got picked several times. That's completely okay. We may even be able to pick 2 or 3 points at a time or pick them in batches or all of them at the same time. But for simplicity, we're going to stick to picking 1 point at a time. So here's the next question. What do we have to do to move a line closer to a point? So basically, if this is our point and this is our line and the point says come closer, what is the mathematical way of doing this? So for this, we move to the Cartesian plane where we have the horizontal or x-axis and the vertical or y-axis. Here's our point, here's our line, and the point says come closer. So lines have two parameters that define them. The first one is the slope, and the slope basically tells us how steep this line is. To calculate the slope, we just take this distance divided by this distance. So the vertical distance divided by the horizontal distance. This is constant across the line, no matter where we measure it. And that tells us how steep the line is. And the other parameter is the y-intercept, which is this distance. It basically says how high does your line touch the y-axis or the vertical axis. And if we have these two numbers, the slope and the y-intercept, we can reconstruct any line. This is unique. And the idea is to move the line in this direction. So what we're going to do is we're going to move the slope and the y-intercept in the way that helps us the most. So we're basically going to do a rotation and a translation. So let's look at rotation. Rotation is the same as changing the slope, because if the slope is this, if we want to rotate the line counterclockwise, we just increase the slope, because the bigger the slope, the steeper the line is. And if we want to rotate the line clockwise, then we just decrease the slope. And the rotation happens around this point here. This is the pivot. It's the point where the line intersects the y or the vertical axis. So now let's look at translation. Translation is the same as changing the y-intercept. The y-intercept is this point over here where the line meets the y-axis. And so if we want to translate the line up to a parallel line that is higher, all we have to do is increase the y-intercept, because now the line meets the y-axis in a higher place. And if we want to translate the line down, then we just make this y-intercept smaller. So that's it. That's how we do translation and rotation. So let's summarize. This is the cheat sheet for moving a line. To rotate the line counterclockwise, which is doing this, we want to increase the slope. In order to rotate the line clockwise, which is doing this, we want to decrease the slope. In order to translate the line up, which is doing this, we want to increase the y-intercept. And in order to translate the line down, which is doing this, we want to decrease the y-intercept. So now, depending on where the point is and where the line is, we're going to do a combination of the correct rotation and the correct translation in order to move the line closer to our point. So we end up with 4 cases. Here's the first one. Let's say the point is over here and the point says come closer. So for that, we want to rotate the line counterclockwise like this and then translate it up like this. That is equivalent to increasing the slope and increasing the y-intercept. Now, if the point is over here and want it to come closer, notice that now we have to rotate the line clockwise like this and translate up. Rotating clockwise means decreasing the slope, and translating up means increasing the y-intercept. Now, what if the point is down here? Then we want to rotate the line counterclockwise and translate down. So rotate the line counterclockwise like this and translate down. That's the same as increasing the slope again and decreasing the y-intercept. And finally, if the point is over here, then we want to rotate the line clockwise like this and translate down like this. That's equivalent to decreasing the slope and decreasing the y-intercept. So as you can see, all these 4 cases are different. And here's a summary of the 4 cases. We have 4 regions: blue, red, yellow, and green. And the way to define these regions is if you are above or below the line and to the right or to the left of the y-axis, because remember the rotation pivot is at the point where the line and the y-axis meet. So that's why we have these 4 regions. And for each of the regions, we have the instructions increase or decrease slope and increase or decrease y-intercept in order to move the line closer to the point if the point is in one of those regions. So let's get a little bit more mathematical about how to move a line. Here's our point again, our line, and the point says come closer, so we want to move the line in this direction. So a line always comes with an equation. For example, an equation like y equals 2x plus 3. If you've seen y equals mx plus b, this is it. So the 2 is the slope and the 3 is the y-intercept. Now this line is obviously not drawn at scale because a slope 2 line will be a lot steeper, but just for visual simplicity, we drew it like this. And so this is how we're going to modify the 2 and the 3 in order to move the line closer to the point. So here is a very important rule of machine learning. You don't want to make any drastic steps. You don't want to move the line by a lot. We want to move it a very tiny amount because we're going to do this many times. So a way to make sure that we're doing things in a very small amount is to multiply them by a small number. So we're going to pick a small number. That's step 1. It's going to be called the learning rate, and this appears everywhere in machine learning. It really just means you want to make tiny steps. So we pick a small number. Let's pick a random small number. I went for 0.01. And now basically what we're going to do is just add the small number to the slope and the y-intercept, add it or subtracting depending on where the point is. So step 2, in this case, the point is above the line and to the right of the y-axis. So we're actually going to add the learning rate to the slope and the learning rate to the y-intercept. So what do we do? To the 2, we add a 0.01, and to the 3, we add a 0.01, and we get the line 2.01x plus 3.01. And since it has a bigger slope, then it's been rotated counterclockwise, and since it has a bigger y-intercept, then it's been translated up, so it's somewhere around here. Again, this is not drawn at scale, it's probably much closer, but this is just for visual simplicity. And as I mentioned, I said add and add, but it would really be add and subtract, or subtract and add, or subtract and subtract, depending on where the point is located. So let me summarize that in the next slide, where I show you the entire algorithm. So here is a linear regression algorithm to fit a line. Here we have our points. Step 1, we start with a random line. Here's a random line. And we're going to do steps to make this line better and better. So another thing is machine learning is we're going to repeat something many times. How many times? Well, let's pick a large number, that number of times. So it's going to be the number of repetitions or the number of epochs. Whenever you see the word epochs in machine learning, that's what this means. So my favorite big number, let's say it's 1,000. Step 3 is what we just did before. We pick a small number, which is the learning rate, to see how small is our step going to be. Step 4 is a big loop. So we're going to repeat something many times. So we're going to repeat it 1,000 times, the number of epochs. And what are we going to repeat? First, we're going to pick a random point. The point says come closer, so we're going to move the line towards the point. So let's remember that the long rule to move a line towards the point is this. If the point is above the line and to the right, then rotate counterclockwise, translate up, etc., etc. 4 cases. Like we saw before, each case corresponds to either adding or subtracting something to the y-intercept and to the slope. So here's the rule. Feel free to pause this slide and take a careful look at these 4 cases and convince yourself that this is how it works. And so when we do step 4, this is what happens. We move the line closer to that particular point. And since step 4 is repeated 1,000 times, then we pick another point, we do the steps to move closer to that point, and we keep going and going and going 8,000 times until we get something pretty good. We may have to fiddle with that 1,000 and maybe make it bigger, depending on how accurate we want to go and how much running time we have. And finally, step 5 is enjoy your fitted line. So that's it. That's an algorithm for linear regression. I encourage you to code it. This is the pseudocode here, so code it and see how it works with some simple data sets. So that algorithm works. I've actually coded and tried in some simple data sets and it has decent results. However, we can still do better. We can still do better in 2 ways. The first one is performance. We can actually come up with an algorithm that works better and converges quicker to the correct line. But the second one is simplicity. If you look at that algorithm, it has too many cases. The point has to be here or here or here, and then you add, subtract. That's complicated. What we're going to do is we're going to come up with an algorithm that is very similar and actually encompasses all those 4 cases into one. This is what I'm going to show you next. So the question, can we do better? The answer is yes. So let's look again at our linear regression algorithm from before. And all of it is simple except for these 4 cases over here. That's too much. The question is, can we turn this into one case? And the answer is yes. So what we're going to do is we're going to define what a positive and negative distance is. And based on this positive and negative numbers, we're just going to summarize these 4 into one case that's very similar and encompasses all 4 of them at the same time. So here's what positive and negative distance is. Let's say we have 2 points at the same height, but with different x-coordinate. And the distance between them is a number, but we're just going to say it's a positive number if it goes from left to right and a negative number if it goes from right to left. So in other words, the distance from the left point to the right point is positive, and the distance from the right point to the left point is negative. And likewise, if we have 2 points that have the same x-coordinate and different heights or different y-coordinates, then we're going to say that the distance taken from the bottom point to the top point is positive, and the distance taken from the top point to the bottom point is negative. Here's an example. Let's say we have these 3 points with coordinates 2, 1, 6, 1, and 6, 4. So what we're going to do to calculate the distance is we're going to subtract the right coordinate, but in a certain order. So if we're going to find the distance between the bottom 2 points, from the left point to the right point, then this is going to be plus 4, because what we're doing is we're taking the x-coordinate and we're subtracting the x-coordinate at the end point minus the first coordinate at the beginning point. And that is 6 minus 2. If you want to do it in the other way around, then we take 2 minus 6, because 2 is the end point and 6 is the beginning point, so that is minus 4. Likewise, if we want to take the distance among the vertical points, then what we do is we take the difference between the y coordinates. So from the bottom point to the top point is going to be 4 minus 1, which is plus 3. And from the top point to the bottom point is going to be 1 minus 4, which is minus 3. So that's how we do positive and negative distances. Notice that we've only defined them for horizontal and vertical distances, because that is all we need. We're not going to need anything with diagonal distances. So now let's go back to our summary with the 4 regions and the instructions on what to do in every one of the regions. And so what we're going to do is we're going to calculate certain distances that are going to be positive and negative for each one of these regions, and they're going to be different. So let's start with the blue region. Here we have a point in the blue region. And the 2 distances we're going to calculate are from the y-axis to the point, and that's positive because it's going to the right. And the other one is from the line to the point, and that is positive because it's going up. So one distance is going to be horizontal, the other one is going to be vertical. And for this case, they're both positive. Now let's go to the red region, which is over here. The distance between the vertical y-axis to the point is negative because it's now going to the left. And the distance from the line to the point is positive because it's going up. Now let's go to the green region. The distance between the y-axis to the point is negative, and the distance between the line to the point is negative because they're going to the left and down. So here they're both negative. And finally, in the yellow region, the distance between the y-axis and the point is positive because it's going to the right, and the distance between the line and the point is negative because it's going down. So here is a summary of all the distances, and in the corners I've written the instructions of what to do to get the line closer to the points. So what we're going to do is we're going to match these pluses and minuses to the increases and decreases. And feel free to pause the slide and think about it yourself. How do you match these pluses and minuses to the increases and decreases? So here's an easy one. Let's look at the y-intercept. So if you are above the line, so for the point in the blue and the red regions, we both want to increase the y-intercept because we want to move the line upwards. And if you look at these 2 signs, they are plus signs because the points are above the line. So these increases match those pluses. And the same thing happens on the bottom. If we look at the 2 decreases for the y-intercept in the yellow and green areas, they match these 2 minus signs. And the reason is that if the points are underneath the line, we want to decrease the y-intercept. So there's one relation that we'll summarize later. And the other one is for the slope. So for the slope is a little more complicated, but what we want to do here is actually take the product of the 2 signs. For example, let's look at these 2. Both of them are plus. And what is the product of plus times plus? So positive times positive is positive. And take a look at this. We want to increase the slope. Now let's go to the red area. We have a positive and a negative. The product of these 2 is negative, and we want to decrease the slope. If we go down to the green area, we have a negative, and the product of these 2 is positive, and we want to increase the slope. And finally, in the yellow area, we have a positive and a negative, and the product of this is negative, and we want to decrease the slope. So there's your relation, and so I'm going to summarize this in this rule, a rule to rule them all. So it says, if I want to rotate a line, then I just take the product of the vertical distance times the horizontal distance, and that's a number that is either positive or negative according to if I want to rotate the line clockwise or counterclockwise. So that's a number that I could add to my slope. And similarly, to translate, if I just take the vertical distance, that's positive or negative according to if you're above the line or below the line. So if I just add that number to the y-intercept, the line moves closer to that point, right? So that works. But let's remember one thing, that in machine learning, we want to make small steps. These numbers are too large. So what we're going to do is we're just going to multiply them by a learning rate and add them. Let me summarize this here. So again, we have our line, our point, and the point says come closer. And recall that the line has equation y equals 2x plus 3. So this is what I call the square trick, and it's a trick to move the line closer to a point. So step 1, we're going to pick a small number, which is the learning rate, just like before. And my favorite small number, let's say it's 0.01. And in step 2, we're going to modify the slope and the y-intercept in a way that will help us. So this is very similar to what we did before, except now we don't want 4 cases, we want just 1. And so here's the idea. To the slope, we decided to add the vertical distance times the horizontal distance, but now we're going to add that times the learning rate. So what is this? This is a tiny number that has the correct sign. It's either positive or negative according to if we want to move the line counterclockwise or clockwise. And similarly, we want to add the learning rate times the vertical distance to the y-intercept. Because as we recall, the vertical distance has the correct sign if you're above or below the line, and the learning rate just makes sure that this number is tiny. So let's do it in this example. Let's calculate the vertical distance. So the vertical distance here is positive because this particular point is above the line, and the horizontal distance is also positive because the point happens to be to the right of the y-axis. So let's throw in some numbers. Let's say that the vertical distance is plus 3 and that the horizontal distance is plus 5. So how are we going to modify the slope? Well, we're going to add the product of learning rate times vertical distance times horizontal distance. That's 0.01 times 3 times 5, which is plus 0.15. And how are we going to modify the y-intercept? Well, we're going to add the learning rate times the vertical distance, which is 0.01 times 3. That's 0.03. So our new line has equation y equals 2.15x plus 3.03. The slope is 2.15, so it's bigger than 2. That means that the line has been rotated counterclockwise. And the y-intercept is 3.03, which is bigger than 3, which means the line has been translated up. So we get something like this. Something that is closer to the point. There are 4 cases to check to make sure that this square trick works well. I'm going to check just another one more. Let's check the one where the point is below the line and still to the right of the y-axis. So the point has come closer. This is the equation again. Step 1 is again pick a small number. Learning rate is 0.01. Step 2 is add this to the slope and this to the y-intercept. So now the vertical distance is negative because the point is underneath the line. Let's say it's minus 4. And the horizontal distance is still positive because the point is to the right of the y-axis. So let's say it's plus 5. So how do we modify the slope, this 2 here? Well, we add 0.01 times minus 4 times 5. Notice that the minus 4 makes this number negative. So the whole number is negative. It's minus 0.2. So by adding minus 0.2, we're actually decreasing the slope, which is exactly what we want because we want the line to move clockwise. Now, what are we going to do to the y-intercept? Well, we're going to add the learning rate times the vertical distance, which is 0.01 times minus 4. So we're going to be subtracting something because we're adding a negative number. This is minus 0.04. So our new line has equation 1.8, which is 2 minus 0.2, x plus 2.96, which is 3 minus 0.04. So notice that the slope is smaller, which means the line has been rotated clockwise, and the y-intercept is smaller, which means the line has been translated down. So we get something like this, which is closer to the point. Now we only checked 2 of the 4 cases, but I encourage you to check all of them and see that step 2 works consistently for all of them. So finally we are ready to look at a linear regression algorithm. So it's going to go like this. We want to fit a line to these points. Step 1, start with some random line. Step 2, pick a large number. That's the number of repetitions we're going to do, number of epochs, 8,000. Step 3, pick a small number, the length of our step, so 0.01. That's the learning rate. So step 4 is going to be a loop. We're going to repeat the number of epochs times, so 1,000 times. Pick a random point. We want to listen to the point. The point says come closer. And now we're going to move the line towards the point. So remember that the rule for moving a line towards a point is add learning rate times vertical distance times horizontal distance to the slope, and learning rate times vertical distance to the y-intercept. So we do that and the point moves closer. Since we're repeating this 1,000 times, then this is what happens. It moves and moves and moves until we're done. And step 5 is enjoy your fitted line. And that's it. That's the linear regression algorithm. Again, I encourage you to code it. The pseudocode is right here, and test it on some data sets and see how it works. So this second algorithm works really, really well. I've tried it on some data sets, and it works beautifully. So now a question pops in our mind. Is this better than the existing algorithms? Or is it the same as the existing algorithms? And that actually reminds me of someone I once worked with, a very brilliant mathematician called John Borwein. And one of the things he did was he tried to find digits of pi, etc. So in particular, he wanted to find like different expressions of pi, like formulas that would give you pi. And whenever he found a formula that was really close to pi, he would say, well, this is a win-win situation, because either I found a new formula for pi, or I found something that's really close to pi that is also very special. So in here, I'm thinking we have a win-win situation because we have an algorithm. Either it's better than the existing ones, or it's actually the same as the existing ones and way more simple. And so actually it turns out to be the second one. This algorithm is the exact same algorithm that is used for linear regression if you've heard of square error, gradient descent, etc. This is what I'm going to show you next in the 2 challenges that I have for you. So here are the 2 challenges I have for you. The first one is regarding the square error. So remember that at the beginning I told you that there is a traditional way to do linear regression, which is considering an error and making it smaller, etc. This is what I'm talking about. So here are some points, and we're going to try to fit a line to them. So here's an attempt. This attempt is terrible. This line is really bad because it doesn't fit the points. So let's try again. Here are our points again, and what about this line? So this line is much better. This is the good line. However, as humans, we can eyeball these very easily. We can see that the line in the left is better than the line in the right. But for a computer, this is not easy. They have a hard time doing this. So what we need to do is come up with a measure that is different for the bad line and the good line. In particular, we're going to come up with an error function, a measurement of how bad the line is, that is big for the line in the left and small for the line in the right. And what we're going to do is we're going to measure badness with orange. So the more orange, the worse. The way we measure here is we take the distance from the point to the line, the vertical distance, take that segment and make a square out of that. And then add the areas of the squares. So you can see that for the bad line, these squares are pretty big because the points are pretty far from the line. So that's a large square error. We're gonna call it a square error. And now for a line that is good, well, that line goes really close to the points. So you can imagine that the square is much smaller because the squares are much smaller. So we have a small square error. And the idea is that we're going to go from the large square error to the small square error using mathematics. And in math, you can minimize functions using derivatives, using calculus, gradient descent, or even just solving a linear system of equations. So this is the traditional method. The most popular is gradient descent because it's the fastest. And so the question is, how does this algorithm compare to our algorithm, our square trick? And you'll be surprised to see that it's actually the same thing. And so the challenge here is to verify this, to actually go ahead and calculate these square error by taking the distances and squaring them, and then taking the derivative and taking a small step in the direction opposite to the derivative, which is what gradient descent does, and verifying that is the same thing we did in the square trick. And the idea is that this derivative of the square difference actually has a lot to do with the vertical and horizontal distances. So that is the first challenge. The second challenge regards the absolute error. So remember that I told you that there are more than one ways to measure the badness and the goodness of a line. The first one was the squares, and this one is much simpler. It's actually just adding these segments, just the lengths, not the positive or negative lengths, but the actual absolute values of the lengths. That's why it's called absolute error. And notice that for the bad line, the points are far, so the sum of orange distances is big, whereas for the good line, the sum of orange distances is small because the line passes much closer to the points. So you can do the same thing as we did before, minimizing using calculus. And if you want to actually go for it, check out what happens when you do a gradient descent step on this error. So what trick comes out, and you can actually develop an absolute trick. And I'll tell you the answer. This is the absolute trick. So this one only deals with the horizontal distance. It doesn't care about the vertical distance, but it does have one if statement, which is if the point is above or below the line. And if the point is above the line, then you add learning rate times horizontal distance to the slope and learning rate to the y-intercept. And if it's below, then you just subtract them, and you can convince yourself that the horizontal distance takes care of the sine of what you're adding to the slope. So you can convince that this yourself that this works. And again, I would encourage you to code this one. So I think that's all over here. I'd like to remind you that this is a series of 3 videos. So this is the one about linear regression, and we're going to develop very similar tricks for logistic regression and support vector machines. So stay tuned. And that's all, folks. Thank you very much. As usual, if you like this video, please subscribe or hit like or share. And I love it when you comment, so please add in some comments, questions, suggestions. Tell me how you did with the challenges. And in particular, if you have suggestions for other videos you'd like to see, please tell me in the comments. And you can also hit me up on Twitter. My handle is LewisLikesMath. So thank you very much, and see you in the next video.